Hello everyone, this is Siavash Ibrahimian. Today I'm going to talk about our group project. This group project is a result of the great collaboration and fabulous team working with Mr. Alan Matthew and Trey Woods. Our group project is about researching, designing, simulating, and calculating the gate valve API 6A. Today I'm going to talk about the introduction. It means what the gate valve API 6A is. Also, I'm going to talk about the gate valve design criteria, schematic diagram with label, and talk about different components in the gate valve. Also, in our project, we have done the stress analysis with the SolidWorks finite element analysis, FEA, as well as we did the fluid mechanics with the computational fluid dynamics on ANSYS softwares, and we have done thermal analysis on SolidWorks, as well as we have done the mathematical engineering hand calculations, either in fluid mechanics and solid mechanics. Introduction. So we know our project is a gate valve. The other name of the gate valve is a sluice valve. The gate valve is opened linearly by lifting the gate disc and directly connected to the stem that regulates by the actuator. The gate valve is open and closed linearly, that means goes up and down, moving up and down. The gate valve is connected with the stem. In our project, the stem is threaded with the gate, and the gate is opening and closing with the actuator. Actuator is regulating the gate or disc. You know, the other name of the gate is disc. The gate valve is a bidirectional slab valve that is the ideal valve for the high pressure. Our project is a high pressure and a high temperature. And that's the reason we use the API 6A. AP, the stands for of API is the American Petroleum Institute. We have two API. We have one API 6A that we have used for our project, and we have an API 6D. The API 6D is mostly used in a petrochemical and refinery industry. However, the API 6A standard is commonly used in a subsea, submarine, offshore, and oil and gas industry. And the mechanical components of a gate valve API 6A is manufactured with the most advanced machine tools to achieve dimensional accuracy and machining tolerance. Also, the 6A is mostly produced by machining techniques. However, the 6D is mostly produced with a die casting method. So, in our project, to complete the design of a gate valve API 6A, it must be simulated with the finite element analysis to analyze the volumetric stress, which is also called the distortion energy, and as well as analyzing displacement or deformation. Also, we have done the computational fluid dynamics, CFD, to analyze the erosion issue. And also we have done the thermal analysis to show the temperature distribution result, and doing manual engineering calculations to verify fluid dynamics and FE analysis. For the fluid dynamics, we have used the fluid mechanics equations, and for the FE analysis manual hand calculations, we have used the solid mechanics equations. So our flange-to-flange gate valve has a specific design criteria that we have to follow all those specific characters, specific criteria to design our project, to design our part properly. For example, the internal diameter of our design is 2.9/16 inches, which is equal to the 65.1 millimeter. The working pressure is 10,000 psi, testing pressure is 15,000 psi, and the material class is FF. So based on this table, The FF material class is a stainless steel. That means we have to use stainless steel material for our valve body and bonnet and different components of our project. So we know the test pressure is a 15,000 psi. So based on this table, the 15,000 psi, the yield strength of the body and bonnet must be 45,000, 60,000, or 75,000 psi. Therefore, we decided to choose AISI 410 stainless steel for our project. So AISI stands for is the American Iron Steel Institute. 410 stainless steel, the yield strength is a 6,200 psi, which is in range of a 6,000 psi based on this table that I provided on this slide. So, and also this elastic modulus is a 30, around 30 mega psi, pound per square inches. The Poisson's ratio is a 0.285. Shear modulus is around 12 mega psi. Mass density is a 0.2836. Tensile strength is equal to the 74,000 psi. We use these material properties, we use these mechanical properties on a SolidWorks material properties. That means we got these material properties on the SolidWorks material criteria. Also, in our design, the temperature class is a P350 Fahrenheit degree. P shows the minimum temperature, and 350 Fahrenheit shows the maximum temperature. The PSL level in our project is level number 4. The stands for PSL is a product specification level, and the product rating PR level in our project is level number 2. So the PSL, we know PSL stands for is a product specification level. This one defines different levels of technical quality requirements. You know, we have 4 levels of PSL. PSL level number 1, 2, 3, and 4. Our project, we use a level number 4. In PSL level number 4, we are doing some testing, including temperature testing, chemical classifications, material classification testing, heat treatment, tensile testing, and as well as impact testing. We do all this testing to make sure our project, our design, our manufacturing final product is working properly. Also, in PSL level number 4, the manufacturers should document the material chemistry, material classification, melting, and industry standards to utilize the final product. What is the final product? Final product is when all components assembles each other. And also, based on this table, the welding is not permitted except for the cladding. What the cladding is? The cladding is the weld overlay. Also, based on this table that you are seeing on the right-hand side, also for the overlay or cladding or weld overlay, the repair weld is not permitted. So product rating is used for testing and validating the assembly product. The product rating level number 2 is one of the hardest testing criteria that includes the validate both design and the final valve product. As I said, what is the final valve product? The final valve product is the assembling all different components of the valve design, of the gate valve. So in the product, based on this table, the product rating level number 2, the operating cycle is equal to 200 cycles. What does 200 cycle means? It means we open and close 200 times. We tested 200 times to open and close the gate to make sure the gate valve is working well, to make sure the gate valve is is fully open or fully closed to make sure the gate valve is working 100% well. So in this slides, I'm gonna talk about and show different component of the gate valve from the top to bottom. So the toppest part is the actuator. We know actuator is the part to regulate the gate, to open and close the gate. We know the actuator is connecting to the stem, and then stem is connected to the gate. In our project, the stem is threaded with the gate. Also, thread has two parts. Sorry, stem has two parts. One is a thread section, and other one is an on-thread section. On-thread section is a place where the bushing, the green color, and the packing is located. So the bushing that we use, the material usually is a polytetrafluoroethylene or graphite. And the packing that we use is a Chevron V packing. So we use these materials to control the external pressure to prevent the stem and bonnet from damages. Also, this part is a actuator base which connected with the actuator with the bolts. This is the bolt. And also for designing the bolt, we use a specific equation. We use a specific formulas to designing the bolt. And this is the energizer plate. This is energizer plate. So energizer plate has a has a bolt, knot, sorry, has a knot, this part and the purple part. And the bonnet. So we know the bonnet is the second most important component of the gate valve. And these are other bolt, the size, the ID, internal diameter and external diameter of the bolt. This bolt is different from this bolt that connect the actuator and the actuator base. And this is a seat, which is between the gate and the disc or the valve body, and metal-to-metal seal. So in our project, we use a metal-to-metal seal because our project is a high pressure and high temperature. We use the 4 metal-to-metal seals here, 1, 2, 3, and 4, which is located between the seat and the valve body. And also we use the 2 metal-to-metal seals, which is located between the valve body and the bonnet. So we use the metal-to-metal seals to prevent all damages from the high pressure and high temperature. That means we prevent the gate, valve body, and bonnet from damages that comes from the high pressure and high temperature. The blue color is the valve body, and this is the flanges. And the left-hand side picture is a half-section view of the gate valve. Shows exactly all components of the gate valve API 6A. And this is the other view of the gate valve. This is the other view of the gate valve API 6A. So these slides, I'm gonna talk about the final element analysis of the valve body, the pressure vessels analysis for the body. So we know the testing pressure is at 15,000 PSI. And the material that we have used is a AISI 410, that the yield strength is a 60,200 PSI. So we know the maximum stresses occurs at the corners. That is shown here. So this is the inside of the gate valve, has the 4 corners, and all high pressures occurs at these edges, 1, 2, 3, 4. And this red color shows where the fluid is affecting to the valve body. These arrows are the internal pressure that comes from the fluid that's passing through the valve body. And the green color, this green color shows the fixture area that we fix these 2 places to doing the FEA on the SolidWorks. FEA and SolidWorks, and the fixture area are located on the flanges. So anyway, the high stresses occurs at the corner of the corner. Along the mesh boundary, therefore, the peaks can be disregarded. So the internal diameter of the valve body is a 2/9/6 inches, which is the part of the design criteria of our project, which is equal to 65.1 millimeters. The external diameter, the OD that we have decided to design for our valve body is a 4 inches, which is equal to the 101.6 inches. The thickness is equal to the 1.4375 inches, which is equal to 36.5 millimeters. The material yield strength is 60,200 psi because we use the AI, we have chosen to use the AISI 14 stainless steel. And the rating factor is a 0.9, allowable stress is a 54,180 psi, maximum stress is a 37,700 psi, so, and the safety factor is a 1.44. So the maximum stress, which is equal to this 37,700 psi, is here, the red color. The red color, which is the internal pressure, is the place where the fluid is passing through the valve body. So the pressure occurs to the valve body is the internal pressure. The green color is the average, which is the between the minimum and maximum pressure, and the blue color shows the minimum pressure. So this green color, as I said, this is the place where the fixture area is located. The fixture area is located on the flanges of the valve body. So this slide is a manual, is a mathematical hand calculations. We use the solid mechanics equations. So in a hand calculations, we need to determine is equivalent stress equal or less than the maximum yield strength or not. So if equivalent stress is less than or equal to maximum yield strength, it means our design successfully passed. That means we have designed our component wonderful and it works properly well. So for calculating the equivalent stress, we need to calculate the hoop stress, radial stress, and longitudinal stress. So before I talk about the hoop stress, radial stress, and longitudinal stress, we need for the design, so the thickness is very important. The external diameter is very important. So the body wall thickness is equal to the external diameter minus internal diameter divided by 2, which is equal to 0.7185 inches, is equal to the 18.25 millimeters. The ratio of thickness is equal to thickness divided by the internal diameter is equal to 0.2803 inches, is equal to 7.12 millimeters. The hoop stress is equal to the testing pressure times the external diameter square plus internal diameter square divided by the OD square minus ID square, which is equal to 35,895.84 PSI. And the radial stress is exactly opposite of the testing pressure, which is equal to the negative 15,000 PSI. And also the longitudinal stress is equal to the testing pressure times ID square, internal diameter square, divided by the OD square minus ID square. And so which is equal to the 10,447.907 PSI. So equivalent stress based on this equation that you are seeing, which is 1/10 square root of 2, then times square root of these equations, the Hoover stress minus radial stress square plus radial stress minus Hoover stress square plus longitudinal stress minus Hoover stress square, which is equal to the 44,077.068 psi, which is less than the 6,200 psi. What it means? It means our design is 100% correct, and it means our product is working properly well, is working 100% wonderful, without no issue, no technical issue, as well as in mathematical engineering calculations, hand calculations, we have solved the check percent allowable, which is equal to the equivalent stress divided by the allowable stress times 100%, 100, which is equal to the 81.35%. So this picture is a half section view of the valve body. And so we know also the temperature, the rating factor, as I said, is equal to the 0.9. So in this slide is about the thermal analysis. This slide is testing with the maximum temperature. We know our design criteria, the temperature class is a P350 Fahrenheit degree. 350 Fahrenheit degree is a maximum temperatures. So in our material properties, our convection coefficient is equal to the 500 British thermal unit per hour times feet square times Fahrenheit degree. So we have used a thermal analysis to see how temperature is distributing to the different components of the gate valve. The red color shows the maximum temperature, it shows the hot fluid with the temperature at 350 degrees passing through inside the gate valve. And this shows exactly all arrows. And the blue is a minimum temperature, is a room temperature, is around the room temperature, which is equal to the 86,976 Fahrenheit degree. That the table is provided on the left-hand side. Here we know the temperature, the room temperature is 77 Fahrenheit degree, but it's close to the room temperature. And the green color is the average between minimum and maximum temperature. The average temperature is equal to 178.632 Fahrenheit degree. And also the table also is provided here, shows from the minimum all the way to the maximum temperature, which is equal to 350 Fahrenheit degree. So this slide is a minimum temperature simulation. So we know P shows the minimum temperature. Based on this table, the minimum temperature is equal to the negative 20 Fahrenheit degree. So we use the cool temperature at minimum temperature to negative 200 Fahrenheit degree that passes through the inside the gate valve. The blue color shows the minimum temperature, which is negative 20 Fahrenheit degree, which is here. And the red color or orange color shows the maximum temperature, which is equal to the 67.044 Fahrenheit degree, shows the from minimum all the way to the orange color or red color, the maximum temperature. So also, this maximum temperature is close to the room temperature. We know the room temperature is 77 Fahrenheit degree. When we apply the minimum temperature, the maximum temperature becomes 67.044 Fahrenheit degree in our thermal analysis. And the average temperature is equal to the 36.713 Fahrenheit degree. Also, as I said, in our project, the material property, the convection coefficient in our material property is equal to the 500 British thermal unit divided by the hour times feet square times Fahrenheit. So this slide is about the bonnet and bolt. Before we talk about the design, talk about the specific of the design of the bonnet, I'd like to talk about briefly about the bonnet. So we know the bonnet is the second main part of the valve to retain pressure. We know bonnet and the valve body are retaining pressure. However, The stem and the gate or disc are controlling pressure, because with the gate, because we close and open the gate by the actuator, because the gate is controlling the pressure and the gate is directly connected with the stem. But the bonnet and the valve body are retaining the pressure. Anyway, bonnet is connected to the valve with the bolt. So in some designs, the bonnet is connected with the valve with the threaded or welded. But in our project, we decided to connect the bonnet with the valve body with the bolt. And the bonnet is produced either by cast or forged. And the bonnet can be very complicated in manufacturing. And because for the valve size and the cost, significant cost, and the leakage, we have to design a bonnet that has a very good, has a high quality sealing, have very less less properly to have a leakage. So we have to design to have a zero leakage with a high quality sealing. So the bonnet material is AISI 410 stainless steel. The material that the yield strength is 6,200 psi. Bolt material is the AISI 304 stainless steel. That the yield strength is 90,000 psi. 90,000 psi is the yield strength for the bolt. And the base on this table, the bonnet force that we have applied is around 2 mega newtons. The number of a bolt that we have used is 12. The external diameter is 1 inches. Bolt force is 175,420.6667 newtons. Material yield stress is equal to the 90,000 psi for the bolt, and the multiplier is 0.83. Allowable stress for the bolt is equal to the 74,700 psi, and the maximum stress that has applied to the bolt is equal to the 50,213 psi, and the safety factor is equal to the 1.49. So before I go to the next slides, the first main component of the gate valve is the valve body. Second main component is a bonnet, and the third main component is the gate or disc. So we know all components of the gate valve are important, but gate valve body, bonnet, and the gate are the first, second, and third main component of the gate valve. So energizing of packing. So energizer plate, this is energizer plate, and the bushing that is connected with the bushing and the packing. So we use the bushing material and V-packing and energizer plate to retaining the pressure, to controlling the external pressure that comes from the fluid and different components. So the bushing material is a polytetrafluoroethylene or graphite. Energizer plate material is 304 stainless steel. This part does not encounter high stress, and is so low yield material is allowable. This is the ISO International Standard Organization view, and this is a cutaway view of the energizing of packing. So the metal-to-metal seals. We use the metal-to-metal seals in our project because our project is a high pressure and high temperature. We use the metal-to-metal seals to protect the body and bonnet from the high pressure and high temperature. Metal-to-metal seals will be placed between the seat and body. We use the 4 metal-to-metal seals between seat and body, And we use two metal-to-metal seals between the body and bonnet. The material that we have used is a stainless steel, that the AISI stainless steel, that the yield strength is equal to the 45,000 psi. We use a metal-to-metal seal to prevent damage to the valve, and a soft material is preferred. Seal is designed to ultimate strength of the material. Low yield strength material is preferred. So these two arrows are shown the small raised section on the metal-to-metal seals that the bodies will deform and seal against. This design of seal energizes the metal-to-metal contact further while operating. The pressure causes the formation of the chevron shape, allowing higher sealing. So this is a FE, the final element analysis for the metal-to-metal seals. The red color shows the maximum one message stress, which is equal to the 55,000 psi, and the blue color shows the minimum one message stress, which is equal to the 1,222 psi. And the green color shows the average, shows the between the minimum and maximum one message stress. So in these slides, I'm going to talk about the design criteria of a gate. We know the gate is the third main part of the gate valve. So design criteria of a gate including good finishing, and the surface of the gate must be smooth, must be flat, and must be parallel with sitting surface. Why it must be parallel with sitting surface? Because when the gate is fully closed or fully open, this whole surface of the seat must contact with the surface of the gate. Because if the seat and the gate 100% contact and touch with each other, that means we have a high quality ceilings. That means we have a low probability leakage in our design from the gate. As well as our gate is connected with the stem with the threaded. Also, we do the gate deflection and stress to make sure our design is working properly. The thickness of our gate is at 3.5 inches. Sorry, it's 3.5 inches, and the total height of our design, of our gate design, is equal to the 9.84 inches, which is equal to the 24 or 25 centimeters. Exactly, is a 249 millimeters, which is equal to the 24.9936 millimeters. And the right side picture is the meshing analysis of the gate valve. So this slide shows the final element analysis when the gate is fully closed. The red color shows the maximum pressure that comes from the fluid, because when the gate is closed, the all fluid is pressuring to the gate, to the surface of the gate. So the maximum one message stress is equal to the 9,169 psi. The minimum one message stress is equal to the 5,048 psi, and the average is equal to the 6,470 psi. So the blue color shows the minimum one message stress, and the maximum shows the red color shows the maximum one message stress. And I use the AISI 410 stainless steel. These 410 stainless steel, the yield strength is equal to the 42,000 psi. And this picture shows the displacement, shows the deflection, the formation. So when the gate is closed, all fluid pressure is pressuring to this place of the gate. The red color shows the maximum displacement, and these arrows shows the arrows that the pressure, the fluid is pressuring, or direction of the fluid to the gate. So if you want to know our design is working well, is correct 100%, the deflection, the deformation must be in range between 0.001 inches to 0.002 inches. So the maximum deflection in our design, in our stress analysis on the FEA and SolidWorks is equal to the 0.00116 inches. That means our design is 100% correct. That means our design is working properly. And the minimum stress is equal to the 0.0006 inches, has a 3 zeros before 6. And the average is equal to the 9.9191 times 10 to the positive negative 4 inches, which is equal to the 0.0009 inches. Blue color, this blue color shows the minimum displacement, and the green color shows the maximum displacement. And the green color here is a fixture point. On the SolidWorks FEA, we decided the fixture area on the place where when the stem is threaded with the gate, and where the seat is located around where the seat is located. So the green color here that shows here is a place where the seat is located and touches 100%, touches completely with the surface of the gate. Second slide is about doing the final element analysis on the SolidWorks when the gate is fully open. So when the gate is fully open, all fluid is pressuring inside the gate. And this red color shows the arrows, this red arrow shows the internal pressure that come from the fluid. And this ring shows exactly where the seat is located and where the seat is touching the surface of the gate. And these green arrows shows the fixture area, as well as these green arrows shows the fixture area where the stem is threaded with the gate. So in this situation, the maximum volume stress is equal to the 6.207 times 10 to the positive 4 psi. The minimum is equal to 2.028 times 10 to the positive 4 psi. And average is 3.197 times 10 to the positive 4 psi. And also these other graph shows from minimum volume all the way through the maximum volume stress. We know the other name of a volume stress is a distortion energy. So right side picture shows the displacement. So we know the maximum displacement must be in range between 0.001 inches to 0.002 inches. So in this situation, when the gate is fully open, the maximum displacement is equal to 0.002059 inches. This is correct. This is a little, very a little higher than the range, but that is good. That is wonderful. And the minimum displacement is equal to the 3.937 times 10 to the negative 32 inches. Very low displacement. And the average is a 9.167 times 10 to the negative 4 inches. The reason we have a low displacement because of the material that we have chosen, the stainless steel with the yield strength 42,000 psi, thickness, and the thickness and the height of the gate or disc. So all these criteria are important to determine the volume stress and displacement or deformation. So here I provided the video to show the step-by-step of the to show the step-by-step of the FEA simulation processes of the volume stresses. And here shows the minimum, maximum, and average volume stress. Here, that's here. Anyway, and the next slide This is a video of the SolidWorks FEA simulation process. Shows a step-by-step of a displacement from the red color, which is the maximum displacement, the blue color, which is the minimum displacement. And the red color shows the maximum, shows the pressure, maximum pressure from the fluid that is pressuring to the gate when the gate is closing. So these two videos that I provided are the videos when the gate is fully closed. So here, this slide is about the packing. What the packing is the reliable seal between the stem and the bonnet, and the gasket is needed for our packing. Valve packing must be properly designed and produced to prevent damages to the stem and bonnet. If the packing is too loose, the valve will leakage. And if the packing is too tight, it will affect to the movement and possible damage to the stem and bonnet. The material that we use for the packing is a chevron V packing. And also the copper coating is used to prevent the friction resistance between stem and packing. So we use the copper coating to prevent the friction between the stem and packing, because we know the packing, so before the packing, the ID of the packing is the 31 millimeters, and the ID and the diameter of the stem is the 30 millimeter. That's the reason we designed 31 millimeter ID for the packing to exactly fit with the stem. And with the stem, we know the packing is located between the stem and the bonnet. We use the packing to prevent any damages from the bonnet and the stem. We use the copper coating. That's the reason to prevent any friction resistance between the stem and packing. And also, in our assembly parts for the packing, we use one male and two middle parts and one females. And when we assemble one male, two middle parts and one females, the total height is equal to the 2.27 inches. And the material that we have used for the chevron V packing is a polytetrafluoroethylene, PTFE, in our design. So this slide is about doing the final element analysis of the stem and actuator. So we know we need the higher force than the acting on the gate to make sure the stem and actuator is working properly. That's the reason we use a higher value force in our testing. And the torque applied is at 600 Newton meters, and operating torque is 400 Newton meters, and provides a safety factor of 1.5 meters. Sorry. The safety factor is a unitless, and the value is a 1.5. And this is a video to show the final element analysis of the stem and the actuator. And this shows how open this direction is a counterclockwise to open the gate. So clockwise is closing the gate, counterclockwise is opening the gate. So here the maximum deflection is equal to the 0.459 millimeters, and the minimum deflection is a 0. There is no minimum deflection. And the maximum volumetric stress is equal to 96 megapascal, and the minimum is a 0 megapascal. And the yield strength, the material for the stem and actuator, is equal to the 620 megapascal. This slide is about the computation fluid dynamic simulation. This is a meshing analysis on the ANSYS. So we use the ANSYS software to do the computational fluid dynamics. So we use 4 different velocities to determine the Reynolds numbers with 2 different fluid. We use the steam fluid and the propane fluid. So for the density of the steam is equal to 0.5542 kilogram per cubic meter, and the dynamic viscosity for the steam is equal to the 1.34 times 10 to the negative 5 kilogram per meter second. So this slide shows we have video to show step by step of the velocity streamline for the 50 meter per second and the 70 meter per second when the gate is fully open. So the maximum shows from the 0 velocity to the maximum velocity, which is 51.639 9 meter per second. And this is the other video when the gate is fully open, shows exactly step by step of the pathway of the fluid when the gate is fully open at the 70 meter per second. So this slide shows the step by step of the gate when the gate is partially open for the steam fluid. This video shows the fluid velocity at 5 meter per second when the gate is partially open. And this one shows for the 50 meter per second when the gate is partially open. You see the gate is partially open. There's a small part of the gate is open. And exactly show, all colors shows the maximum and minimum pressure, maximum and minimum velocities, maximum and minimum stresses, or pressures that come from the fluid. And also this slide shows the pictures of the partially open when the fluid is the propane, C3H8, and the dynamic viscosity of the propane is equal to the 7.95 times 10 to the negative 6 kilogram per meter times second, and density for the propane is equal to the 1.91 kilogram per cubic meter. And also, these are other picture of the CFD on the ANSYS when the gate is partially open. Have a pressure counter. These are 2 pictures for the 5 meter per second and the 100 meter per second when the gate is partially open, and it shows the pressures from the minimum negative 450 Pascal to the maximum, which is equal to the 1713.620 Pascal. As well as this one shows the minimum pressure, which is equal to the 173, negative 173 Pascal, to the maximum pressure, which is equal to the 696,664 Pascal. So this slide shows the wall shear stress at the 50 meter per second, shows the liquid nitrogen, propane, and the water vapor. Exactly show the step-by-step of the fluid pathway on an ANSYS. So the minimum, the pressure is 0.01 Pascal, and the maximum pressure for the liquid nitrogen is equal to 308.14 Pascal. For the propane, the minimum is 0.01 Pascal, and the maximum is 263.66 Pascal, and for the water vapor or the steam is equal to the 5.15 times 10 to the negative 3 Pascal, and the maximum pressure is equal to the 264 Pascal. The roughness factor of 0.015 used for the stainless steel material to measure frictional drag and much higher wall shear stress due to the turbulence caused by the disruption of flow and higher viscosity. This slide shows the mathematical hand calculations to calculate the Reynolds number from the steam fluid and propane. We use this equation from the fluid mechanics equation. We calculate the Reynolds number with 4 different velocities, including the 5 meter per second, 15 meter per second, 70 meter per second, and 100 meter per second for both steam fluid and propane. And the equation of the Reynolds number is equal to the density times velocity times internal diameter. You know, the internal diameter of our design of the valve body is equal to the 65.1 millimeters. Then divided by the dynamic viscosity. We know the ID is a constant number, V is a variant, and the density and dynamic viscosity is also variant. Depends on the material. Depends on the steam fluid and propane. And also, in our design, we have to follow some design criteria, and they are the rules. They are the policies. So in next 2 slides, I'm gonna briefly talk about these policies that we have followed, that we have used in our design criteria. One of them is a hydrostatic seat testing that obtained from API 6A, American Petroleum Institute 6A. So in this hydrostatic seat testing, we apply the hydrostatic seat test pressure, which is equal to the rated working pressure to one side of the gate or plug of the valve, with the other side open to atmosphere. So after the pressure has been applied to one side of the gate or plug, hold the pressure and monitor for at least 3 minutes. Then open the valve while under full differential pressure. Repeat the above 2 steps with a minimum of 15 minutes holding times. Test is bidirectional valve. You know, our gate valve is a bidirectional. Gate valve, one of the properties of the gate valve is a bidirectional in both directions. And test unidirectional valves in the direction indicated on the body. After when we have done all these steps, finally we pressurize one side of the gate or plug, hold and monitor a 3rd time for a minimum of 3 minutes. And test by directional valve, the next test by directional valves on the other side of the gate or plug using the same procedure outlined above. And the next criteria that we follow in our design is a gas seat testing obtained for our project API 6A, gate valve API 6A. Apply gas pressure on each side of the gate or plug a bidirectional valve with the other side open to the atmosphere. Test unidirectional valves in the direction indicated on the body. Conduct the test at ambient temperatures using nitrogen as the test medium. Conduct the test with the equipment completely submerged in a water bath. Testing shall consist of 2 monitored holding periods. The primary test pressures shall equal rated working pressure. The primary test monitored holding period shall be 60 minutes. Reduce the pressure to 0 between the primary and secondary holding periods. The secondary test pressure shall be greater than 5% and shall be less than the 10%, between 5 and 10%, the related working pressure. So already I talked about the primary, and also the second test primary, the second test monitor holding period shall be 60 minutes. The valve shall be fully open and fully closed between tests. Finally, test bidirectional valves on the other side of the gate or plug using the same procedure outlined above. Last 2 slides about the testings, about the testing that we follow, that we have to follow in our design to make sure to have a 100% correct design, to make sure our design is working properly. So for designing the components, we have to follow design criteria. We have to follow the standards. Those design criteria and standards makes our project, makes our final product, makes our assembly parts work wonderful, makes our product professional. So those standards, those design criteria are the most important in our project, in our designing, you know. So that's it. Thank you so much, everybody. Thank you so much for your listening. Thank you so much for your patience, and have a wonderful and fabulous day. See you later.